Okay, this is live lecture number 14. We're in Calculus 3, November 9th. So you see here is the agenda for today's class. A lot of stuff to cover. I'm going to kind of go through these solutions more or less fast, but if you feel like you need me to slow down, definitely let me know. But I would like to make sure we cover everything that's on the agenda. Let's go ahead and just jump right into the new material. So scalar line integrals. What is the basic idea of line integrals? Let's say we're working with a surface, okay? So we're working with a function of multivariables, okay? So let's say we have f of x, y. That's a surface that sits in 3 space, okay? And we used to integrate this surface over a domain or part of a domain. So let's say we would compute integrals of this function over something like a rectangle, okay? So this would be our area of integration. And we said, okay, we're really computing a volume under this surface over this rectangle, right? So if we do this projection here, okay, and say, well, what is the volume of this object right here? That's the integral. And we know how to set this up, how to evaluate such integrals. That's what we've done last week. So today we're going to talk about a different kind of integral where we're integrating over a line, and it really should be named curve integrals because it's very rare that we're integrating over a straight line. Okay, so what if I were to integrate my function over a directed curve? So let's say we start at some t value, and usually t represents time. So let's say we go from t0 to t1, okay, and we have a directed curve. So if we have an object traveling on this curve, it will be going that way. All right. So here's my curve, and I would like to integrate my function over this curve. Okay. So we're not going to go through the rigorous derivation of the formula. You see the formula down here, but I would like for you to have this intuition of what is it that we're computing. One way you can think about it as we're computing or approximating the area of a curtain. Now, if you project this onto your surface and then kind of think about this curtain that follows this curve right here. That's what we're computing. And there are many applications in physics for computing line integrals. So one such thing would be computing mass. Okay, if you have a density function and you're integrating it over a curve, really what we're computing is the mass. So that's just one quick interpretation of what line integrals are. So let's go ahead and jump into computations, and you'll see that these are not too bad. And we've done parts of computations in actually in calculus 2 when we were trying to find line integral, the length of the length of a curve. So again, one more thing you can kind of relate to. We know how to compute this length right here, right? So what if we were to just compute the length of this line segment? Okay, then you can think about it as integrating one, your constant function one, over this curve, and that will give you the length. So that's like a reduced version of the line integral. It will give you exactly the same format as we've already discussed in this class and in calculus 2, computing the length of a curve. So let's take a look at the first example. Okay, what does it say? It says evaluate the line integral of f along C, and C is defined to be what? This is a circle of radius 3, and it's centered at the origin, right? Okay, centered at 0, 0. Okay, so we're integrating our function over this curve right here. Okay, let's say this is 3. So let me go ahead and give it an orientation. Okay, so that's my circle. And now let's go ahead and talk about some components. This function right here, let's make sure that we realize this is a scalar function, right? This is not a vector function. This is a scalar function, thus the name, scalar line integrals. And this will be important as we introduce more and more types of integrals. Okay, what is the idea here? Let's take a look at the formula. It says rewrite your line integral now in terms of a parameter t. Notice there's no x, no y. Everything is in terms of t. And it all depends how we write our parameterization of c. Our c stands for curve, right? So c is for curve. Okay. Now this curve is easy to parameterize, right? We know what the parameterization of a circle is, okay? So C in terms of parameter T, what is it? Okay, you can think about it as x is equal to 3 cosine t, y is equal to 3 sine t, okay? And then t, if we want an entire circle that goes from 0 to 2 pi. Okay, as a vector valued function, we can write this as 3 cosine t for the x component and 3 sine t for the y component, and t is still in the same range, okay, from 0 to 2 pi. So now we know how to parameterize our circle, okay? Now the next step is to take our function y squared plus x squared and rewrite it in terms of t, okay? Let's go ahead and do that. So f of xy, what is it in terms of t? Well, x is 3 cosine t, so that's 3 cosine t squared plus y is 3 sine t, right? So that's 3 sine t squared. Okay. And what do we get? We actually get a nice Pythagorean identity, right? So this is 9 cosine squared t plus 9 sine squared of t, and that, of course, is equal to just 9. Okay. All right, so that is our function in terms of t. That's done. Okay, so which part did we just do of the formula? Let's look at the formula. We just did this part right here. We rewrote our function in terms of the parameter t. Okay, so now we need that length of the curve, right? That's what the other part is. Okay, that's just the magnitude of this of the velocity, which is just the speed of the object moving, right? So here we go. So what is it that we need? We need, oops. Okay, so this is the magnitude of r prime of t. That's all it is. That's just by definition. Okay, so what is r prime in this case? That's going to be negative 3 sine t, and we square that, plus positive 3 cosine t, that's also squared, and square root of that. Okay, so that turns out to be square root of 9, which is 3. And now we can put all the pieces together. So what is this integral equal to? Our line integral. And right here, we're writing C for curve, so that represents line integrals. Okay, f ds, that's like compact notation for your line integral. What is it? It's an integral that goes from 0 to 2 pi. F of t is equal to what? That's 9. And times 3 dt. Oh, that's nice. That's really easy to integrate, right? This is just a constant function. Okay, so we integrate in 27. Now we just got to multiply it by 2 pi. Okay, so 27 times 2 pi, that gives us 54 pi. Okay, all right. So let me stop right here and just kind of briefly go through all the steps. Okay, I have my function, I have C. C is not given to me in terms of a parameter t, so that's my very first step, to rewrite my curve in terms of t. Once that's done, I rewrite my function in terms of t as well. Okay, then I compute um, the velocity, okay, and then compute the speed, put it all together in one formula, carefully evaluate, and you can see that the integration itself is not very complicated. All right. Okay, so let me stop right here, take a look at this. Let me know if there's anything you would like to discuss for this problem. I see a thumbs up from Corey, so I think that most of you guys are doing okay, right? So let's go ahead and keep going. All right, let's take a look at a similar problem, except now we have a function of 3 variables. Okay, no problem. The idea will be exactly the same. In this case, r is given to us in terms of a parameter. Okay, so r of t is given to us as a vector function. Okay, so one less step for us to do. All right, now that we know what c is in terms of parameter t, we can just go ahead and rewrite our function f in terms of t. Okay, let's see. X is equal to 3t, y is equal to 7 cosine of 4t over 7, and z is equal to 7 sine of 4t over 7. Okay, so the function is pretty simple. Okay, so that's our f of t. Now we compute r prime. What is it in this case? This is 3 times what? Okay, so this would be negative, right? The derivative of cosine is negative sine. And then 7 times the derivative of the inside, which is 4 over 7. So that 7 is gone. That's going to be negative 4 sine of 4t over 7. Okay. And then over here, similarly, we're going to get 4 cosine of 4t over 7. Okay, I forgot to mention that I'm missing my values of t here. Okay, so t goes from 0 to 7 pi over 4. That's given in the problem. I just didn't, I forgot to type this in. So add that as part of the statement of the problem. Okay, and you can see how, oh, that's nice. That's going to give us very nice computations um, once we start plugging them in. All right, so that's r prime of t. Okay, what do we do next? Next, we compute the speed. So this is the magnitude of this vector. It's a little messy, but it will work out. Okay, so this is 3 squared plus 16 sine squared of this argument plus 16 times cosine squared, same argument, right? And we take square root of this. Now, this is just a fancy long way of writing 16. Okay. 16 plus 9, that's 25. So we get 5. Oh, look at that. 5 right here and right here. It's going to cancel out. Okay. This kind of gives you the confirmation that a lot of these problems are reverse engineered, right? To just kind of give you nicer answers at the end. Because if we were just to pick random functions with random parameters, and your answers would be really, really busy and messy. And that's actually what happens in real life, okay? But okay, for a class that's prepped in advance, it's not a bad idea to have more or less nice numbers. Okay, so when you see that, it's a good idea to just kind of say, oh yeah, all right. I think I'm on the right track because all of these numbers line up just right to cancel out. Okay, so now let's go ahead and set this up. Our integral It's a line integral with a representation of C on the bottom. That stands for curve, okay? That's a standard notation that we will be using of f ds, and that's your compact notation. What is it? Let's go ahead and set this up. Our integral goes from 0 to 7 pi over 4, okay? And now I have 3t plus 7 cosine of 4t over 7 plus 7 times sine 4t over 7 divide by 5 times 5 dt. Okay, that 5 is gone, and now I have a very simple integral of just one variable t that goes from 0 to 7 pi over 4. Some things will cancel out, not everything. What's our antiderivative? We can compute that real quick. 3t squared over 2, and then here we'll get 49 over 4 sine of 4t over 7, and then one more thing is going to be negative 49 over 4 cosine of 4t over 7. Okay, we go from 0 to 7 pi over 4. Okay, I'm going to let you evaluate this carefully. The answer is not going to be exactly nice, but it's not completely terrible. So 147 over 32 pi squared plus 49 over 2. That's our final answer. Okay, and we would like to keep these type of answers exact, right? So you don't need to approximate it, just keep it as is. Okay, so let me stop right here for a moment. Take a look at this solution. Let me know if you would like to discuss anything before we move on to line integrals of vector fields. Okay, I see one note from Raymond, no questions, so all good. All right, okay, then this is what we've done so far. Let's go back up here. Scalar line integrals in R2 and in R3. This is what we've done, point number 1. Now we're going into point number 2, line integrals of vector fields. So we'll talk about definitions, applications, and then we'll discuss circulation and flux, which is your physical application of line integrals of vector fields. Okay, let's take a look at the definition first. Line integrals of vector fields. The fundamental difference now is that we're not integrating scalar function. We're integrating vector field, right? So here's your notation right here. F represents a vector field, right? It's F with an arrow, okay? So that's what we've discussed last time, how to construct simple vector fields, what do they look like, and so forth, okay? We still have that R prime of t. Let's take a look at this formula just a little bit. It's not much different from what we just did, except that with vectors, our multiplication is defined differently, right? So if you go back up here, take a look at the formula. We had f of t times the speed, right? Okay, same idea over here, except we no longer do times. It's dot product, right? We have vector functions. So our multiplication of vector functions is now defined as a dot product. Okay, and you can see how we compute the dot product. It's just the sum of the product of the corresponding components. So thus we get this expression right here, f of t times x prime of t, g of t times y prime of t plus h of t times z prime of t. Okay, so that is your formula for computing line integrals of vector fields. Let's go ahead and take a look at the basic integral, and then we'll talk about applications. All right, so the first one says evaluate the line integral of this vector field over a curve r that's already given to us in terms of the parameter t. Okay, so let me just kind of give you this notion that you can think about it. This is x, this is y, and this is z. It's not very obvious right away, okay, but that's how you can think about this parameterization. And we need the value for t. T goes from 0 to 1. All right. Okay, what is our first thing? This should be f with an arrow. That's our vector field. Okay, let's go ahead and rewrite our vector field in terms of t only. Okay, what is it? Sine of x. So that's going to be sine of t cubed. Okay, then I have cosine of y. So that's going to be cosine of negative t squared. And then x times z, x cubed times, I'm sorry, t cubed times t. Okay, I'm going to go ahead and simplify this a little bit. Nothing can be done for the first component. But for the second, cosine is actually an even function. So I can ignore that negative. So this is just cosine of t squared. Now, of course, you can keep that negative in there, but it will make our computations a little bit simpler if we just get rid of that negative. Okay, and then here this is just t to the fourth. All right, so that's our function in terms of t. Then what about r prime? We can compute that. That's 3t squared minus 2t and 1. Okay, now I'm just going to set this up separately before I do the integral. F dot r prime. Okay, what do I get? Okay, so this will be 3t squared sine t cubed plus negative 2t times cosine t squared and plus 1 times t to the fourth, right? So that's t to the fourth. Okay, so that's the function that I'm going to be integrating. Now we can set up our integral. So line integral of this vector field is going to be the integral that goes from 0 to 1 of this function here, 3t squared sine t cubed minus 2t cosine t squared plus t to the fourth dt. Okay, you can see that it's pretty straightforward. You can use the u substitution, but you can also just see what the antiderivatives here are, right? So for the first one, it's going to be negative cosine of t cubed. Okay, then for the second, that's going to be negative sine of t squared, and that's a polynomial one, so that would be t to the fifth over 5. Okay, we're evaluating this from 0 to 1. Now be careful here because not everything is going to vanish at 0, so let's just evaluate this carefully. We're going to get negative cosine of 1 minus sine of 1 plus 1/5. Okay, and then minus minus, that gives us a plus, so that's cosine of 0 plus sine of 0 and minus 0. Okay, so sine of 0 and 0, that's of course gone, but cosine of 0 is actually 1, right? So what is our final answer? Our final answer is going to be, let's see, 1 plus 1 over 5, that's 6/5. And then we get negative cosine of 1 and minus sine of 1. Okay, keep in mind, what is that 1? This is 1 radian, right? Okay, so that's just a value. It's not a table value. All right? So it doesn't turn out to be anything nice, but we'll just keep it as is, okay? 6/5 minus cosine 1 minus sine 1. All right, let me stop right here for a moment. Take a look at this solution. And let me know, guys, if there's anything you'd like to discuss, any questions or comments. No questions? All right, let's keep going. Okay, let's take a look at the following application. This is work done by a force field. Okay, that's one of the applications of line integral. All right, and I think I have a typo here. Yeah, let's get rid of this line right here. Okay, so let's see. We have a force field, xy, 6, 4x, okay, and we're moving along this curve right here from 0 to pi over 2. So how much work is done by the force field, okay, to move an object along this curve? That's one other application of line integrals, okay? Computation is exactly the same. So let's rewrite our vector field in terms of t. Okay, let me remind you that you can think about it. This is x, this is y, and this is z. Okay, so now we can rewrite our vector field in terms of t only. X times y, that's going to be 4, I'm sorry, cosine 4t times sine 4t. Okay, then 6 stays as is. And then 4 times x, that's 4 cosine of 4t. All right, second step, computing r prime. R prime of t is equal to, let's see, this would be negative 4 sine of t. Oh, not t, 4t. The argument doesn't change. Okay, positive 4 cosine of 4t, and here we get 1. Okay, so f is, in terms of t, that's done. We found our r prime. So what is the next step? Find their dot product, right? Okay. All right, so the dot product, what do we get here? We get negative 4, actually, let me write it this way, negative 4 cosine of 4t sine squared of 4t, okay, plus 4 times 6, that's 24 cosine of 4t, and then we get 1 times 4, that would be 4 cosine of 4t. Okay, we can combine these two terms, so we get negative 4 cosine of 4t sine squared of 4t plus 28 cosine of 4t. All right, so we have our function. We need to just evaluate the line integral, right? So work done is then the line integral. We go from 0 to pi over 8, okay? Evaluating which function? Negative 4 cosine of 4t sine squared of 4t plus 28 cosine of 4t dt. Okay, and here the integration is pretty straightforward. Let's see. Can you, again, you can use the u substitution, but you can see that this is just a power rule, right? So this would be sine cube of 4t, okay? And then we need to determine the constant. Let's see. 4 is fine because that's the derivative of 4t, and then cosine is the derivative of sine. But we need to take care of negative and also the power of 3. So negative 1/3 sine cube 4t. That's the antiderivative of the first part. And this one is straightforward. This one will be what? Let's see. The antiderivative of cosine is sine of 4t, and we need to take care of this constant, so this should be 7, because 7 times 4 will give us 28, right? So now we need to evaluate this from 0 to pi over 8. Okay, I'm going to let you fill in the details. The answer here is pretty nice. We're going to get 20 over 3, and that's our final answer for this line integral. So this is the work done on an object by this vector field if we're moving it along this line from 0 to pi over 8. Okay, first application is work. Take a quick look at this solution. Let me know if you would like to discuss anything before we move on to the next application. No questions? Okay, let's go ahead and move on then. Let's take a look at the next application, which is circulation of a vector field. So before we do any computation, let's actually discuss what circulation is. So what is the circulation? Okay, you might have some intuition of what a circulation is, but it is how much of a vector field, how much of a vector field, I'm going to abbreviate it VF, is going in the same direction as the curve. Okay, that's kind of your intuitive definition of what circulation is. So it's going in the same direction as the oriented curve. Okay. All right, so we're basically going along the curve, the vector field, or is it going against it? Okay, so let's take a look at the following setup. It says calculate the circulation of F around the closed curve C. C is the counterclockwise path around the circle with radius 2, centered at 6, 4. So let's go ahead and make a quick sketch of what's going on here. Okay, so 6, 4. Here's 6. This is 4. That's my center of the circle, and then the radius is 2. Okay, so what is my curve? What is that going to look like? This is my closed curve, counterclockwise, so it is oriented counterclockwise. This is one way to represent that. Okay, now we're not going to sketch the vector field, but imagine there's actually a vector field sits above this, right? So this vector field right here sits above it. Okay, well, the question is, what's the behavior of this vector field along this curve? Okay, along this curve right here that goes counterclockwise, is most of the vector field, is it going in the same direction, or is it going against that? Okay, so that's your circulation. It's the amount of the vector field going in the same direction as the curve. All right, let's go ahead and compute it. Okay, all it is, it's the line integral. That's it. So business as usual, we need to write our curve in terms of t, except here it's not given to us explicitly, it's given to us as a description of the curve, right? But we know how to write c in terms of parameter t. Okay, And that's why we've done what we did in chapter 12 when we talked about parameterization of curves, standard curves like lines and circles. Okay, let's see. What is it? It's going to be 2 cosine of t plus 6. That's my x. And then for y, it's going to be 2 sine of t plus 4. Okay, we've taken care of the radius, we've taken care of the center, we've also taken care of the orientation. This is important. Orientation matters, right? Because how your vector field is behaving, it's going to be different if you orient it, this curve in a different direction. Okay, so that's important. We know our r prime, r of t. We can compute r prime right away. So what is our r prime? Okay, r prime is going to be negative 2 sine t, and then here we get 2 cosine t. That's r prime. Now we can compute f in terms of t. Let's see, minus x minus y. So negative x minus y. What is that? That's going to be negative 2 cosine t minus 2 sine t, negative 10. Okay, that's my x component for the vector field f. All right, and then the second part is x plus y. So that one is nice. So we get 2 cosine t plus 2 sine t plus 10. All right, now we can compute our dot product, f dot r prime. Okay, let's compute this carefully. Negative 2 sine of t times this. Okay, so times this right here. What do we get? We get a positive quantity, right? So we get 4 sine t cosine t plus 4 sine squared of t, and we get plus 20 sine of t. Okay, plus, what do we get here? Sine squared t plus 4 sine t cosine t and plus 20 cosine t. Okay, let's see what we can do here, if we can simplify anything. All right, this quantity right here, that's just 4, right? Okay, so we can combine some terms here. We get 8 sine t cosine t plus 20 sine t plus 20 cosine t, and then plus 4. All right, and this function is easy to integrate. Okay, so what is the integral now? This is our circulation, right? So let me write it. Circulation of the vector field f around this curve. What is it? It is the integral. Where are we going? Okay, we're going from 0 to 2 pi, right? So that's our circle right here. We go from 0 to 2 pi for t. 0 to pi. Okay. The dot product we've computed already. 8 sine t cosine t plus 20 sine t plus 20 cosine t plus 4. This is very straightforward integration. There are no tricks here. Everything is straightforward. You can do the u substitution for the first part, or you can just see that it's a power rule, right? You can apply the power rule here. The answer is very nice. Again, I'm going to let you fill in the details here. The answer is going to be 8 pi. Okay. All right. So most of the vector field, a lot of the vector field, right, it's a positive value, is going in the same direction as that curve. Okay, so that's your second application of line integrals of vector fields. Okay, as usual, take a moment, review this solution before we move on to the next problem. Let me know if there's anything you would like to discuss. All right, doesn't look like we have any questions. Okay, so let me go back up here to see where we are. So for line integrals of vector field, we know what our definition is. We looked at work done. We've done the circulation part, and now we're going to talk about flux. Okay. And some of you who are taking physics, you are familiar with this concept. Okay, computing the flux of F across C. Okay, so an intuitive definition of what a flux is the amount of stuff passing through a surface. This is how I think about the this concept. So the amount of stuff passing through the surface. Okay. So that's another application of line integral. All right, so let's see how we compute that. Okay, for this one, we do need a new formula that we're going to compute. To compute the flux of F across C, okay, we're going to need the following formula. F of t times y prime of t minus g of t times x prime of t. And there is a name for this quantity right here, and we're going to make this connection a little bit later in our course. So next week, we'll actually give this a name, and you'll see how these two concepts are connected. But for now, we just need to kind of keep in mind that we need to compute the line integral of this quantity right here. And we have the path for our problem is not smooth, but it's piecewise smooth. So we have this rectangle, right? So counterclockwise path around the rectangle with vertices 0, 0, 4, 0, 4, 6, and 0, 0, 6. So let's go ahead and make a sketch of this curve that we're going to be working with. Okay, so let's see, we go from 0, 0 to 4, 0. And then we're going to go up to 4, 6. And then we're going to go to 0, 6, and then come back to 0, 0. So we have 4 lines where we need to compute our flux on. Okay, it's oriented, so we start at 0, 0, and then we go in this direction. Now, our definition applies to smooth curves. This is not a smooth curve, right? Because we have these corners at the vertices. No problem. That just means we need to split up our computation in 4 parts. This is what we call a piecewise smooth. Okay, this curve right here, the C is piecewise smooth. Okay, and in this case, we just split up our computation in 4 parts. All right, so this solution is going to be fairly long because what it means, now we need to find the parametric description of all of these curves. Okay, let me go ahead and label them so we can refer them to a little bit easier. So the first one is going to be curve number 1, then this is curve number 2, curve number 3, and curve number 4. Okay, so how do we do this computation? All right, let's go ahead and take a look. Let's work with curve number 1. Okay, this is still a line integral, so we need to know what our parameterization of our curve is. Okay, what is R1 of t? R1 of t is a line segment, a straight line segment that goes from 0 to 4. Okay, so in terms of vector valued function, that's just from t to 0, right? Because the y component is fixed. The y component is just 0. And t goes from 0 to 4. Okay, that's our R. Okay, so now we need to apply this formula that I have in red. Okay, so this is your y and this is your x. Let's keep that in mind. So now we can apply our formula to compute that quantity. Okay, so f of t, what is f of t? F of t is equal to x plus y, right? So this would be t plus 0, and that's just t. Okay, what about g of t? I'm looking at my original function right here, right here. This is my function, right? So g of t is x times y. So that would be t times 0. So that's 0. Okay. All right. What about y prime of t? Y prime of t is 0 prime. That's 0. X prime of t, that's t prime. That's 1. Okay. Then from here, f of t times y prime of t minus g of t times x prime of t. What is that going to be? That's going to be t times 0 minus 0 times 1, and that's 0. Okay? If we integrate 0 over anything, we're just going to get 0. So on C1, we can stop right here. The flux is equal to 0. Okay? All right, so that's the first part, and yes, we gotta do everything of the same type computations for the other 3 curves. All right, so let's see what happens on the next curve. So this is going to be on C2. What happens on C2? We got a right parametric description of our curve. It's a straight line that goes from what does it go from? 0, 4, and it goes to I'm sorry, 4, 0 to 4, 6, right? Okay, so what's fixed? The x component is going to be fixed, and the y component is the one that's changing. Okay, so that's going to be 4t, and t now goes from 0 to 6. Okay, so let me remind you again that this is x, this is y. So now we can write our little functions, like our f function. What is our f of t? X plus y, that's 4 plus t. G of t is x times y, so that's 4t. Y prime is going to be 1. X prime is going to be 0. Okay, now we can compute that quantity. F times y prime, that's 4 plus t times 1 minus 4t times 0. And now we do not have a 0 function. We have a linear function 4 plus t, and that's what we're going to integrate now. Okay, integrate over what? Then you go back and say, okay, what is my parameter changing here? Like it's going from 0 to 6. Okay, so we're integrating from 0 to 6. This function right here, 4 plus t dt, not a difficult computation. We go from 0 to 6. Okay, at 0 everything vanishes, so just evaluate this at 6, and we get a nice number, 42. So the flux on C2 is non-zero, okay, positive amount, okay, of stuff going through the surface along that line. All right. Okay, before we finish C2 and C4, does this make sense to you guys? Do you see what I'm doing? I know I'm kind of going fast, but there's a lot of stuff to cover, but I want to make sure that you're all keeping up with the computations. So let me know. And you can use the chat. Okay, I see a couple of thumbs up, so then we're good to go. Let's go ahead and finish this problem. All right, C3. What happens on C3? Let's take a look. On C3, we have y coordinate is fixed, right? So y coordinate is 6. X is the one that's changing. So what is our parameterization going to look like here? Okay, it goes from 4 to 0. So we're going to go with 4 minus t 6. And now t goes from 0 to 4. And you can plug in what happens at t is equal to 0. At t is equal to 0, we're at that vertex 4, 6. And at t is equal to 4, we're in our final destination, the point 0, 6. Okay? So that's our parameterization. So once again, we write our function f of t. That one is x plus y. So that will be 10 minus t. Okay. What about g of t? That one is x times y. So that's going to be 24 minus 6t. Okay. Let's see. Y prime is 6 prime. That's 0. X prime of t, that's going to be negative 1. Let's put all of this together. F times y prime, that's 10 minus t times 0, minus 24 minus 6t times negative 1. So that's going to be minus minus gives us a plus. We're going to get 24 minus 6t. Okay. What is the integral here? We go from 0 to 4, 24 minus 6t dt. Pretty simple to integrate, right? So this is 24t minus, what is this, 3t squared, right? We go from 0 to 4, and we're going to get 48. Okay. All right, so that's what happens on C3. Okay, for C4, okay, for C4, I'm going to ask you to complete on your own, but I will give you the answer. Complete on your own whenever you get a moment. Okay, the answer for C4 is going to be negative. Okay, so negative 18. All right, and then we can compute total flux. Okay, what is it? 0 plus 42 plus 48 minus 18. We add them all up and we get 72. Okay, so this solution right here is pretty involved, right? Lots of stuff that kind of come together in one problem. Parameterization, integration, this quantity right here that we're going to give it a name. And then, this is an application problem as well. And you might be saying, oh, there's got to be an easier way to compute this. And there is, okay? There's definitely a nicer, quicker, easier way to compute this quantity. We're going to discuss that next week. All right, but this is the long way of computing line integral over a curve that is not smooth, but it's piecewise smooth, right? So anytime you have a corner like that, or you have a cusp, maybe there is a cusp, right? Then we got to split it up. We're going to split it up and rewrite our parameterization for each of the part of the curve. It's a little tedious, right? But it is doable. So let me stop here for a moment. Take a look at this and let me know if there's anything you would like to discuss before we move on to our next topic. No questions? Okay, then let's see. We are done then with this second part right here, line integrals of vector fields. We talked about the definition, a couple of applications, circulation, and flux. So now we're going to talk about conservative vector fields, what they are, how we can determine if a field is conservative, and what's the connection between phi, the potential function, and how do we find it. And then if we have time, we're going to take a look at the fundamental theorem for line integrals. If we do run out of time, that's okay. I'll have a quick session then on Thursday. All right, let's see. We'll start with the definition. Conservative vector field is a vector field on a region of R2 or R3 if there is such a function phi that if I take the gradient of this function, that gives me the vector field in question. Okay, so vector fields that are called conservative. Conservative comes from conservation of energy. Okay, it is not the political affiliation of this term, right? So conservation of energy related to physics. Okay, let's go ahead and make this claim right here. Not every vector field is conservative. This is important. Not every vector field is conservative. There are a lot more vector fields that are not conservative. Okay, keep that in mind because there are some theorems that we can apply only to conservative vector fields. Okay, so this is going to be important. Okay, these vector fields are special. They have properties that not applicable to vector fields that are not conservative. Okay, so one way to think about it, a vector field um, is this a derivative of something, right? Is this a derivative of a potential function? Okay, and that's all not always going to be the case. So how do we test for conservative vector field? If we have a vector field in R2, then we only need to check one condition, that the partial df dy is equal to dg dx. Okay, and then for R3, if you have a vector field that is with three components, then we have to check this pairwise. Right now there are three components, so we need to make sure that these partial derivatives are the same pairwise. So there are three conditions to check. And of course, you can extend it. You can extend it to R4 and R5 and finite dimensional vector spaces, except that we're only going to stick with R2 and R3. Okay, so let's go ahead and take a look at the following example. Determine if this vector field is conservative. If the answer is yes, that means there is a potential function phi that generates our vector field. So if the answer is yes, let's go ahead and compute it. Okay, I'm looking at my function here. Okay, my vector field is in R2, right? We have two components. So this is F and this is G. I need to check one condition. dF dy, is that equal to dg dx? Okay, if the answer is yes, then I should be able to determine a potential function phi. Okay, if the answer is no, then we say no, the vector field is not conservative. We stop right there. So dF dy, what is that? It is the partial derivative with respect to y of which quantity? 2x cosine y minus y cosine x. And what do we get here? We get negative 2x sine y and then minus cosine x. Okay, that is my partial of f with respect to y. What about partial of g with respect to x? That's the partial derivative of the following function, negative x squared sine y minus sine x. With respect to x now, right? So negative 2x sine y minus cosine x. Yes, they are identical. Okay, that means there is a potential function phi that generates this vector field as its gradient field. Okay, so now the question is, what is that phi of xy? What is it? Okay, we need to compute this function so that the gradient of phi is equal to our vector field. Okay, let me make this question mark a little bit nicer. What is that phi right here? Okay, so let's see. How do we compute this? What do you guys think? You guys have any ideas on how to determine this function? I want to see if you have an intuition that tells you how to compute that function. What kind of operation do we need to use? So Sergey says we got to integrate. Yes, because we took derivatives, right? When we're computing gradient, we're taking derivatives, we're taking partial derivatives with respect to x and with respect to y of the same function, right? So to undo that operation, we need to integrate. So let's integrate one at a time. Okay, I'm going to integrate my x component. So, the function that represented with f. Okay, so 2x cosine y minus y cosine x. I'm going to integrate this with respect to x. Why x? Because if I start with a potential function phi, that component is found by differentiating with respect to x. To undo this, I'm going to integrate it with respect to x. Okay? If that's the case, I'm going to get what? What am I going to get? I'm going to get x squared cosine y, okay, minus y sine x, and plus what? Plus some constant, right? Now, constant in this case is going to be a function of y. Why is that? Because if I were to differentiate anything that just has y, then it's going to be gone, right? Because we treat it as a constant, okay? So really, this is a function of y, okay? And now I can integrate the second function, negative x squared sine y minus sine x. Now I'm going to integrate this with respect to y. Why do we do this? Because that g was determined by computing the partial derivative with respect to y of our original function phi. So to undo this operation, we need to integrate with respect to that same variable. All right, so what do we get here? The antiderivative of negative sign, that would be positive cosine. So we get x squared cosine y. And you can already see that they're lining up. Okay, what happens here? Minus sine of x. That's just a constant. The antiderivative of that with respect to y is just y sine of x plus some constant in terms of x, okay? And you can see right here that these functions match up exactly, okay? So what is our function phi? There is actually a whole family of functions whose gradient will be our vector field, okay? What is that function going to look like? X squared cosine y minus y sine x plus, and let's give this constant k, where k is a true constant, just a number, right? Okay, that's just a number. You can check that if you were to compute the gradient of phi, you're going to get our vector field f. Okay, all right. So let's take a look at the full solution of what we've done here. The first thing that we did, we computed our we applied our test, okay, to determine if the vector field is indeed conservative. Okay, the answer is yes, this equation is satisfied. So now we need to find the function phi. Okay, so we integrate each of the components of the vector field with respect to the correct variable. All right, keep in mind that now our constants are not just numbers, they're constant functions depending on which variable that you're working with. So for the first one, it's c of y. For the second one, it's c of x, but it turns out to be that it's just a constant variable, so just a number. All right, so let me stop right here for a moment. Take a look at the solution and let me know if there's anything you would like to discuss. All right, if there are no questions, let's now take a look at a vector field in R3. Okay, same idea, determine if f is conservative. If it is, compute phi. Now let me give you just a quick little warning. Sometimes on a test, I will tell students, okay, this vector field is conservative. Show that it's conservative and then compute phi. And then I get students who somehow end up showing that it's not conservative. Okay. If you see that I'm telling you it's conservative, it is conservative, 100%. Okay, there is no question about it. Okay, now if it says something like determine if it's conservative, yeah, then it could be conservative, maybe not. But whenever I tell you, yes, it is indeed conservative, make sure your computations are correct. Okay, so if it doesn't work out, go back and check. Oh, maybe you computed a partial incorrectly. All right, so what do we need to show here? Okay, let's go ahead and label our functions. I'm going to label them as f, g, and h. So f, g, and h. And we need to show the following. Partial of f with respect to y, okay, is the same as partial of g with respect to x. That's one equation. Then partial of f with respect to z is equal to partial of h with respect to x. Okay, so right now these are question marks. Is that true? I don't know. We'll find out. And then dg dz, is that the same as dh dy? Okay, all three need to be satisfied. If two are satisfied and one is not, the answer is no. F is not conservative. Okay. All right, let's see. df dy. What is that? df dy. I'm going to get 2x. All right. dg dx is also 2x. Okay. So the first equation is good to go. All right. The FDZ, what do we get here? The FDZ is 2Z. The HDZ, I'm sorry, the HDX, not DZ. The HDX is also negative 2Z. Okay, so we are good here. So far, so good. Last one, DGDZ, 2. DHDY is also 2. Okay, all three are satisfied. All right, we can say that F is conservative. Okay, that means phi exists. Okay, all right. What do we do? Same steps as in our previous problem, except now we need to integrate 3 times. Okay, first one, the integral of what? We're doing 2xy minus z squared. We're going to integrate this with respect to x. Okay, what do we get? We get x squared y minus z squared x and plus what? What does our constant is going to look like? Our constant is going to be a function of 2 variables, y and z, right? Relative to x, this is just a constant. So it could be a function. But when we're integrating or differentiating with respect to x, it's just a constant. All right. So let's compute them all and then we'll line them up and inspect our answers. Second part, x squared plus 2z, we're integrating this with respect to y. Okay, that's going to be x squared y plus 2zy plus constant function of what variables? X and z. Okay, let me check this. X squared y plus 2zy plus c. Okay, and then the last part, we're going to integrate 2y minus 2xz with respect to z. What do we get? 2zy minus x z squared plus constant in terms of which 2 variables? So now we have x and y. Okay, and now if you carefully inspect, you'll see what's going to happen here. So x y squared plus z minus z squared x. So I'm going to look at this first part right here. Okay, what is this function c of y and z? That's just 2zy, right? And then if we take a look at the next one, x squared plus 2zy, c of xz, what is this function right here? Okay, x and z, that's just going to be negative z squared x. And then the last part, let me color it with a different color. Okay, what is our function c of x and y? That's just x squared y. You can see how each, both, all pairs, if you just put them all together as pairs, they have matching components, right? So now we can put it all together as phi, a function of 3 variables, x, y, z. Make sure that everything is there. Okay, so this is going to be x squared y minus z squared x plus, what's our last function here? 2zy. And all of them could just have a constant component k. All right. Okay, that is our potential function, a whole family of functions, so that if I compute the gradient of these functions, I'm going to get my vector field f. Okay, you can check that the gradient of phi is going to be f. All right. Okay, so let's take a look at this solution right here. Let me know if there are any questions and anything you would like to discuss before we take a look at our last concept for today. What do you guys think so far of this whole chapter? Okay, line integrals, line integrals of scalar functions, line integrals of vector fields, then conservative vector fields. Is this, does this make sense? Is it difficult? I know practice always makes it better, right? Okay, but do you follow the basic steps that we've done so far? Yeah? Okay, then let's take a look at our last big concept for today's class. Fundamental theorem for line integrals. Okay, big result, very important. Let's see what it says. We have R is a region in R2 or R3, and we have a function phi that's differential potential function. So these are your keywords here, okay? We've got to make sure that we satisfy all of these conditions. So we have a potential function defined on that region R, okay? So f, vector field f, is the gradient of that function. And this is important. This theorem applies to vector fields that are conservative, okay? Then the line integral over this curve C of our vector field can be just computed as this difference right here, phi of B minus phi of A. And let me go ahead and give you a picture of what's going on here. Let me put it up here. All right, so let's say this is our region R, okay, and we have 2 points, A, B, okay. Our curve goes from A, B, it could look something like that. Okay, so A is the starting point, B is the ending. So for all points A, B in R, and all smooth oriented curves C that go from A to B, okay, so our curve could look something like that. So let's say this is C1. It could also look something like this. Okay, so let's orient it this way. So here I have a piecewise curve, or it could be just a straight line that connects A to B. Okay, and what this theorem says that it doesn't matter which curve you're going to pick. If it's a piecewise smooth oriented curve from A to B, then this line integral over this vector field can be just computed as phi of B minus phi of A. And you can kind of see that this is just an extended version of the fundamental theorem of calculus, right? What did we say our fundamental theorem of calculus one was? When we had an integral from A to B of a function f of x dx, and we had an antiderivative, right? What was our antiderivative? Big F, right? So big F of B minus big F of A. I mean, this is how we evaluate our simple integrals. So here you can see that, oh, our phi, our potential function phi serves as the antiderivative for a higher dimensional version. Okay, so the important things here are, what are the important components of this theorem? We must have a potential function. This does not work. This does not work for vector fields that are not conservative. So if a vector field is not conservative, then you would have to do this whole thing and parameterize all of these steps right here. And then your integral would be different if you were to go along this curve right here. But for vector fields that are conservative, this says that it's path independent. It doesn't matter which way you're gonna go. All it matters is the end points. Okay, let's go ahead and compute the following line integrals in two ways: directly, and then by using the fundamental theorem of line integrals. And that is a problem that I often ask to do to make sure that we grab that big idea. Directly, we can always compute it directly, no matter what our vector fields are. Fundamental theorem of line integrals can only be applied if we're working with vector fields that are conservative, okay? So let's see what we're asked to compute. We're asked to compute this integral right here. How do we do this directly? This is what we learned at the very beginning of today's lecture. Directly, okay? What is our vector field? Well, the gradient of phi, sorry, what is it? It's going to be x, y. That's our vector field, okay? And then we can rewrite our field in terms of t. Okay, parameterization is given to us. So this is sine t, cosine t, and t goes from 0 to pi. That's half a circle. Okay, half a circle, and it's oriented which way? It's clockwise, right? Okay, because you can see that sine and cosine are swapped. All right, so what is our phi? Oh, lambda phi of x and y. Okay, how does that convert to t? That's going to be sine of t cosine t. Okay, that's our vector field in terms of t. We can compute r prime, so business as usual. That's going to be cosine t negative sine t. And we compute our dot product. All right, evaluate it from where? To 0, from 0 to pi. Okay, that's going to be our line integral. All right, what is the dot product? The dot product is going to be sine times cosine, okay, minus cosine times sine, so that's 0, right? If we evaluate this, we still get 0, okay? All right, so one way you can think about it is the circulation around this curve, so none of the vector field is going in that same direction, okay? All right, let's see. How about we apply the second part using fundamental theorem of line integrals, okay? Fundamental theorem of line integrals says, okay, you can just take your function, your antiderivative, and then evaluate it at the end points, okay, just like you were to apply fundamental theorem of calculus. Okay, so phi of pi minus phi of 0, okay, what does that get and what does that equal to? Phi of pi, if I plug that into my function here, that's going to be sine of pi cosine of pi minus phi of what? Sine of 0 cosine of 0. Okay, so sine of 0 is, oh, sine of pi is 0, cosine of pi is -1. All right, so if I plug that in into my function, remember what my function is. So let me remind you what that function is. It's x squared plus y squared over 2. Sine of pi is 0, cosine of pi is -1. Sine of 0, that's 0, cosine of 0, that's 1. Okay, so we get what? 0 squared plus -1 squared over 2 minus 0 squared plus 1 squared over 2. And you can see that that's also equal to 0. We got the same thing, except that in the second part, we did not have to parametric state anything. Okay, there's no need to find parametric description of C, rewrite everything in terms of T, and do all of these steps that we've done for the first part. Okay, so this is a very powerful result. There it is, fundamental theorem for line integrals. Again, I'm going to emphasize how important it is to check that your f is conservative. So you might be saying, what do we do if we don't have a conservative vector field? I checked it, it's not conservative. Then you do the old way. What is the old way? Find the parametric description of the curve, rewrite everything in terms of t, find the dot product, compute that line integral. Okay. All right, so let's see, is that it? That's everything. Okay, let me go back up here, okay, and see what we've done today. A lot of stuff we've covered. So this is a lot of new material. I do not expect you guys to kind of understand it immediately and perfectly and just master everything right away. This is a lot of new material, a lot of heavy new Calc 3 stuff, right? Okay, so definitely take your time going through the problems in the notes, going through the problems on the homework, and then attacking your quiz. Okay, so here's the outline, what we've done. Take a look, see if there's anything you would like me to clarify. And as always, I'm going to stop the lecture and hang out here on Blackboard until you no longer need me. But thank you all for coming. Let me go ahead and stop recording this session.